optimizing cycle inventory, the EOQ model. In order to decide the cycle inventory or manage cycle inventory, we will use the economic order quantity model, for short EOQ, which will allow us to find the quantity Q, order quantity, that will minimize certain cost. Before we introduce the model, let us introduce some parameters. R is the flow rate at which we consume the product. You could think about it as a demand rate for this product. K is a fixed cost per order or per setup if this is like a production setting. H is holding cost, that is holding cost for one unit over a certain unit of time. You know, if you're holding a number of units over 1 year, you can calculate it as, right, what's the cost of holding one unit per 1 year times the number of units you're holding. And Q will be the quantity that we will be deciding, and that will be the product amount that we will order every time. So our pattern of inventory will be receive Q and then use Q at a certain flow rate, and then again receive and then consume and so on. The total cost can be calculated as the sum of two costs that vary now with Q. Remember, Q is our decision. We want to decide how much to order. The rest are parameters over which we have no control. At least we can, we can try to minimize, let's say, cost per order. But once we minimize it, it is a given parameter for this order. The same thing for holding. We're usually determining the holding cost from other reasons, and maybe we optimize it in other settings. So once we have this, we can calculate ordering cost and holding cost and then add them to achieve a total cost. These are expressed per given unit of time, for example, per 1 year. So cost of total cost will be ordering cost. And the first thing to realize here is that R over Q determines the number of orders. And you can see this very easily if you, for example, assume that the demand rate is 1,000 units per year. You will see that if demand rate is 1,000 units per year, then, and let's say if we order Q 100 units, so if our order quantity is always order 100 units, how many times do we have to order every year? Well, we'll order 10 times in order to have enough to satisfy the demand during the year. How did we calculate this? Well, this is actually R over Q, right? R over Q, and this is the number of orders per unit of time, right? R over Q, number of orders per year, right? So R over Q tells us the number of orders per year here, and then multiplying it by K, which is the fixed cost for one order, will give us total ordering cost per year. And then the second part, Q over 2 times H, is the total holding cost per unit of time. How is it calculated? Well, observe that if you order Q and then deplete the inventory down to 0 and then again order Q and deplete it to 0, your inventory varies from 0 to Q, and on average it is going to be Q over 2. So if you calculate a holding cost, we should apply it to the average inventory level Q over 2. Now, some students sometimes tell me that the capital, for example, the cost of capital shouldn't be applied to Q over 2. It should be applied to the full quantity Q, because when we order and receive Q, we have to pay for it, the whole quantity. However, remember that when you manage inventory, you have multiple products and you order them perhaps at different times, replenish them at different times. And the important thing is how much average capital you need for all your inventory. And so imagine that if this product is at a high level, for example, close to maximum, another product might be in an average, another product might be somewhere lower. And so the important measure is what's the, on average, the level of your inventories in total in terms of capital. And you will see that if you have a large number of products, then using Q over 2 as your average inventory level for each product and aggregating over many products will give you a better estimate of the total cost of capital needed, right, to cover this inventory. So for that reason, we use average inventory Q over 2 as an input for calculating holding cost part. So how can we minimize this total cost of ordering and holding? Well, we need to observe that this cost, when we plot it on a chart with respect to quantity Q, which is, remember, our decision, the holding cost will be increasing linearly because it is Q divided by 2 multiplied by the holding cost rate. So, right, how is this changing with Q? Q is here in the numerator and it's just multiplied by a constant divided by 2, which is also a constant. So it is going to be increasing from 0 linearly for any quantity. However, if you look at ordering cost, in this part, Q is in the denominator. So we have a constant R times constant K and then divided by Q. This is going to be decreasing, but decreasing non-linearly, very rapidly for small quantities Q. And then when you increase Q to very large quantities, right, let's say if you change Q to 1,000, changing it to 1,001 is not going to decrease the cost a lot, right? So this is at the decreasing at a changing rate, and the rate of decrease is also decreasing. And so if we add those two, right, think about adding the blue line and the yellow line and finding the function that is the sum of them, right, this total cost of ordering and holding, I hope you can observe that on the left here, when holding cost is small, it's the ordering cost that dominates. And so the total cost will be mainly almost equal to the ordering cost. When you move to the right, it's the holding cost that dominates and the ordering cost becomes close to 0. And again here, right, the increase of the holding cost is going to dominate, and again the cost will be increasing here to the right. So there is somewhere here in between a value that will be the minimum of this function. And this is the value we want to find, and we can actually find it by calculating the first derivative of the total cost of this function. And if we find the first derivative and then make it equal to 0, you should find extreme points, minimums or maximums, because this function has only one minimum and no maximums. That means if you find the point with derivative 0, you will be finding the minimum, the quantity Q at which this cost has a minimum. And I will show you that it happens that this quantity, the quantity that minimizes the total cost, happens at the point where holding and ordering cost are equal. Okay, so let us do some calculations. We said the first derivative, dC of Q, of the cost with respect to Q must be equal to 0. This is when optimal Q that minimizes the total cost will be found. So if in order to calculate the first derivative, we have to see that this is RK divided by Q. Q is the variable is in the denominator, so the derivative will be minus R over Q squared times K plus, and the second part is a linear function, so what will be left will be just a constant half of H. This has to be equal to 0. And let us now multiply this, both sides of this, by minus Q. And you will see that this minus disappears and the 1Q disappears. So what we're left with is R over Q times K. And this becomes negative, but if I move it to the right side, it will become again positive. So I'll write positive Q, right, from the multiplication divided by 2 times H. And notice that what I found here is exactly the formula, the components of the formula here. This is ordering cost, and this is holding cost. And what I found here is that the cost, total cost, is minimized when ordering cost, right, this part, is equal to the holding cost, this part. So that means if you find optimal quantity, you can check in this calculation whether ordering and holding costs are equal. And if they are, you have additional kind of confirmation that your optimal quantity calculation is correct. Now, of course, we didn't still determine what the optimal quantity is. Let me further multiply this by 2Q over H, 2Q over H, right? And let me reverse the side. So I'll take this side first. So if I multiply this by 2Q over H, I'm going to get Q squared, and 2 will disappear and H will disappear. So this side will be Q squared equals, right? And on this side, which will be now reversed, right? We will have Q will disappear. There's division by Q, and I'm multiplying by Q. And what will be left is 2K R. I reversed R and K, and then divided by H, right? So I have Q squared is equal to this. Now, if I want to solve this, I will need to take a root of square root of the right-hand side. But remember, in principle, in math, right, if you solve this equation, Q could be a negative or positive, plus or minus square root of 2K R over H. I can do this because right, the right-hand side, for sure, this part is not negative. It is positive. K is a cost, positive flow rate is positive, holding cost is positive value. So all of these are positive, so I can take the square root. But then Q could be positive or negative, except that, in fact, a quantity that we order can never be negative. It should always be positive. So you can forget about the negativity. It's always positive. And so we get the optimal order quantity. So to summarize, we said if you want to manage cycle inventory, then you can manage it by choosing the appropriate quantity Q. And this quantity should be chosen or can be chosen in order to minimize the total cost that combines ordering cost and holding cost expressed by this formula. So the problem is to find the quantity that minimizes the cost expressed by this formula. And this quantity is Q star equals 2K R over H, and then taking the square root of this calculation. Notice that we already defined that the rate of order, right, number of orders per year is R over Q. We can also invert it and find the cycle time. Q over R will be the length of the cycle, right? It will be how long from the order to the next order, or from receiving to next receiving one order to receiving the next order, the time that it takes. And we can also relate this calculation to the Little's law. Remember, Little's law is I equals R times T, inventory equals flow rate times flow time. Notice that we said average inventory I is Q over 2, right? So average inventory is Q over 2. And average flow time then, from this formula, assuming flow rate is given on constant, can be calculated as I divided by R, which is equal to the cycle time over 2, right? Remember, I divided by R, then you plug in Q over 2 here, so we get actually cycle time divided by 2. So on average, a product spends half the cycle time, and I think it is easy to see if you receive the quantity and immediately you start using some units, some of those units will have very short flow time, but some of those units that you will use here at the end will have a time that they spend almost the whole cycle time in inventory. So average flow time will be cycle time over 2. One more comment I would like to add is related to the time unit that is used in your parameters. Notice that the flow rate is defined per unit of time, and holding cost is also defined per unit of time. You have to make sure before you start doing calculations that those units of times are the same. So for example, if you have flow rate, a number of units per week, but holding cost is a number of dollars per product per year, you have to change either the flow rate to years or holding cost to weeks, right, per week, in order for the model to work correctly, right? So you have to unify the unit of time before you plug in the numbers in this formula and calculate the optimal quantity. If you don't, you're going to get a number that is usually very wrong and is off by sometimes an order or 2 orders of magnitude. And this is one of the typical mistakes in calculations that students do.